Okay, welcome everybody to the second super exciting lecture on AES. So what we did last week, we did only mathematics, which is kind of unusual for this course. Typically we try to do some crypto and some mathematics or some other new concept, but last week we only did Galois fields. And in case you were wondering why do we really need that, you will see that today. So today we're going to talk about the advanced encryption standard, and we're going to need Galois fields eventually today. Maybe one question which we're going to use a lot of graphics today, graphics from the book. Would you like to have the graphics in Blackboard too, so that you can print them out and glue in your lecture notes, or is that a stupid thing? Yes? Okay, we're going to do that. Doesn't cost anything. Okay, so if I don't do it today, remind me or remind Dayun. So what you're going to do today, first I give you an introduction. What is AES? And it's a pretty cool story. AES is a good story. Then we talk a little bit on a higher level about the structure of AES, and then we go into the nasty details of AES, and then towards the end we talk about decryption. Okay, and it's going to be a pretty packed lecture contents-wise, so pay attention, buckle up, don't talk. Okay, except the first one. Okay, so you don't have to pay attention actually. The beginning is just history. Okay, that's unimportant. So first 10 minutes you can sleep. Okay, still don't talk, but sleep. Okay, so okay, introduction. Okay. To AES. Okay, so the very, very brief history, and I think this is one thing that makes cryptography fun. It's a really young discipline. You know, all this stuff happens 10 years ago when you were in school, not in the 1920s, like, so some other subjects that you're learning here. So this is very real, and if you go to a big crypto conference, and those of you who stay here for masters or PhD, you will eventually go to crypto conferences. People are young, they're my age, so it's relatively speaking, okay? So there are very few people over 60. There are many, many people in the 30s and 40s. Okay, so very brief history. In 1997, and if you remember very, very well what we did 2 weeks ago at the end of the DES lecture, we talked about the attacks and what happened in 97, 98, DES was seriously being attacked, so DES was dying, right? And by this time, the US government said, we need a new encryption algorithm. So this was really directly triggered by the fact that DES has become unsecure, okay? So in 1997, there was a call, an Ausschreibung, you would say in Germany, a call for the AES, which stands for Advanced Encryption Standard. DS was the data encryption standard, AES is the advanced encryption standard, called for AES by what's called NIST, which is the National Institute of Standard and Technology. We mentioned that before. So a direct translation would be the DIN in Germany, Deutsches Institut für Normung, but they end up to do, I think they're probably more active than the DIN Institute here. In 1.5 years later or so, in the summer of 1998 was the deadline, and they got 15 algorithm submissions. Which always surprises me. I would have thought they get 50 submissions, but they only got 15. I thought more people would do that, but they didn't. Then 1 year later, in August 1999, they reduced this field of 15 candidates down to 5. So-called finalist, I uppercase as finalist algorithms are selected. So out of the 15 algorithms, they 10 out and 5 are left. These are the AES finalists, and they're all more or less famous in quotation marks. So they're all around, they're all very secure, but only 1 out of the 5 became the AES, was the winner of this process, okay? So we went to 15 to 5, and then it took another 2 years, namely on October 2nd, 2000, which happens to be the birthday of our son Noah, okay, October 2nd, one of the algorithm which was called, and that's not on the exam, okay, so Rheindal, which was one of the name of the algorithms, right? There were 5 algorithms, one was called Rheindal, that's a made-up word by Belgium, that's a Belgium cipher. Rheindal was chosen as the AES. Which was very interesting is that there were the other 4 algorithms, there were some really big prominent names behind it. There was one was by Bruce Schneier, there were Ron Rivest had an algorithm in the field. Most noticeably, there was an algorithm by IBM. And if you might recall that DES was developed by IBM Research in New York. And so IBM had a cipher in that. So I think most people assumed one of the other 4 algorithms would win, but it turned out Rheindal won by 2 young Belgian cryptographers. So that was pretty spectacular, and I guess everybody was very, very happy. The Belgians were very proud, and it was an excellent piece of work. Let me see what else, what data is of interest to you. Let's continue here. The designers, just that we have the names, you know, for it's Allgemeinbildung, you know, everybody should know that. So that was Joan Dahmen, and Vincent Ryman. And we're in touch with Vincent is still at the University of Leuven in Belgium, and we're in touch with them. Oh, actually, we have a very active exchange program with them. So if you're, you know, in your 5th semester, if you want to go abroad and study there, you're welcome to go to the University of Leuven in Belgium or do your bachelor thesis there or your master thesis. So that's a little bit, you know, boring facts. Now we want to start to look a little bit more at the algorithm with a very high level view. So AES is, of course, a block cipher with input, output, and a key, right? This is what, you know, we've seen these type of drawings before. What is of interest are the bit lengths. So this is 128-bit or 16 bytes. 16 bytes is going to be an important thing for this lecture. Does anyone remember how many bits were at DES? What was the bit wide here? The block size? Anybody remember? 64. So this is twice as big. This is not that critical. What is very, very interesting is the key length. You remember DES has 56 bits, which is the reason why DES is unsecure. The key space is too small. Here we have 3 key lengths, and as I showed that last week, namely, and that was part of the NIST requirements. It was part of the call, was part of the Ausschreibung, said we need a block cipher 128-bit length, and you have to support 3 key lengths, which was, I think, at least back then, kind of unusual. What is also unusual is that the number of rounds depend on the key length. That means if you look at the 3 key lengths that exist, which is 128, 192, and 256, the number of rounds, right? You remember DES round, and DES had 16 rounds, and that's it, there was 16. And AES has different number of rounds, so this is number of rounds is for 128-bit, which is the standard bit size for the vast majority of commercial application, you have 10 rounds. If you want to have something more secure for whatever reason, you switch to 192. AES stays the same, but you iterate not 10 times, but 12 times. If you go to 256, you have to iterate 14 times, okay? So this was not a requirement by NIST, this is what the Johan and Vincent did, right? They said if in order for the cipher to be secure, you have to increase the number of rounds if you go with a long key length. Okay. Means whatever happens inside here, you know, the number of rounds is key dependent. So, and before we go into the more technical stuff, I want to give a few final remarks. The first one is maybe the most important one, also for your motivation. AES is by now the most important symmetric algorithm in the world. I don't have any numbers. It's really hard to get numbers, but I'm pretty sure that more than 50% of all data that's being encrypted, at least for new products or products that came out the last 5 or 10 years, use AES. You know, so that's it. This is super important, super important algorithm in terms of practical impact. What you learn in these two semesters is AES is number 1. This is the most widely used algorithm at the moment. Very super important, right? It's not in cell phones. That's bad, but it's in every web browser, right? In Wi-Fi connection, WLAN, all, you know, a million applications use AES. Okay. Second thing I want to mention is when you look at this diagram of this process, you know, there was this call for algorithm and there was a selection process, and it was very exciting. And I started doing crypto in 1995, so we were like a little puzzle piece in this process. So we looked at implementing all these candidates. So there's still some research papers by us where we implemented these 5 algorithms in hardware and then on DSP processors. So I was again a little tiny piece in this whole evaluation process. My question is another one. Was there a similar timeline for the DES selection? 1973, 74, 75. Did we have these dates for DES? No. And why not? So what I want to hear, what was the difference? How was DES selected and how was AES selected? What's it? Wie war das? No. It was done by IBM and top secret. Remember that? There was IBM, probably with input from NSA, developed the algorithm, and then after a few years they said, oh, here's the algorithm. Okay. This was different. There was a public call, people submitted the algorithm, in which what I didn't write down there, people were encouraged, aufgefordert, ermutigt, to analyze the algorithm. That means everybody in the world, every crypto person in the world, they try to break those submissions. They try to break those crypto algorithms. That was a really fun time back then, right? So that was a very super open review process, which is exactly the difference that what happened with DES, okay? What is also interesting is that the NSA, which is a little known fact, but I think it's very, very telling in terms of the evolution of modern cryptography. The NSA, the National Security Agency, what they did until a few years ago, they only used their own algorithm, and pretty much the rest of the world does it too. That means always the intelligence agencies, die Nachrichtendienste, the infosec agencies, they have their own algorithm, and they only use them. So they have their own algorithm. They don't use public algorithm. But what NSA did the same. But what NSA said in now is NSA allows AES for classified, das heißt also als geheim eingestuft, for classified data up to, you know, this is like cheap Hollywood movies, right? But they're real classifications. They're secret and top secret and confidential. And it's up to, and this is always in uppercase letters, so in Großbuchstaben, up to top secret. With, but you have to choose a longer key. So with 192 or 256-bit key. Okay. Again, this is a little known fact. What I think is interesting is NSA, which is this huge agency which has very smart cryptographers employed, they probably think AES is pretty secure. Okay? That means if Obama communicates with the US embassy in Berlin, they encrypt with AES. And of course, you can find it on WikiLeaks later anyway, so, you know. Nevertheless, it's really hard to break it, right? So if there's no WikiLeaks, it's really hard to break. If there's WikiLeaks, you can read it online, okay? So, but still, just the fact that a big intelligence agency said, we trust AES, this is what it says, I think is a pretty strong endorsement for the algorithm. Okay, so this was all Aufwärmübungen, right, for getting started. And it's already just have to squeeze it in. So we're done with number 2, okay? I told you could sleep. This is over now, you have to wake up. Okay, now it's getting interesting here. So now we look at the structure of AES. So this is chapter number 2 of today. Structure of AES. The first statement is, let's do a little bit, stepping back in time by 3 weeks. What was the structure of DES? Können wir ruhig sein hier? Können wir ruhig sein, alle? I told you, wake up and don't talk. When we looked at how DES worked internally on the general type of algorithm was that it was a Feistel network, right? So DES has roughly this structure here, right? This is the main. This is the main kind of viewpoint. How would you call it? Main something rather. So that's the main structure of DES, right? This is a Feistel network, right? This is Feistel. E.g. zum Beispiel DES. And there are a whole bunch of other block ciphers that look that are Feistel networks that have this structure. AES not. AES is not a Feistel network, okay? But AES is not a Feistel cipher. Okay, so it's quite different, which actually makes it very nice that we first introduced DES because many ciphers are Feistel, and now we introduce the different type of ciphers. And one specific feature of Feistel networks is that per round you only encrypt 1/2 of the data path, right? We call this the data path here, right? And here in the case of DES we had 64 bits, but only per round we only encrypt 32 bits, namely those. The other ones are copied over, right, to the next round. And this is not what AES does. AES encrypts all 128 bits of the data path in one round. Okay, so this is not super exciting, but it's a little bit exciting. So let's look at a diagram. That's not the right, that's not what I want to show. Okay. Graphics. No, it's not the right one. Key. Oh, okay, I know where it is. So, and now I give you, this is figure 4.2. This is my book electronically. We're getting close. Okay, here, that's the graphic I wanted to show you. So, okay, so this is the very high level view. Can you read that in the? No, not really. I'll try to blow that up a little bit. Okay. It's better? Is it better? Can you read that, the last row? Billigen Plätze? Yeah? Okay, good. So this is, so I get everything on here. So, see figure 4.2 in the textbook. So this is very important. So this is the equivalence of the DES Feistel thing, right? So this is pretty important. It's to some extent, it's easier. That was a little complicated. What we have here, we just have this difference, they call it layers, Schichten. There's different layers which repeat themselves. And now I want to talk, and I don't want to copy that right now. I'll put that on Blackboard, so you can print that out, and if you want, you can put that in your lecture notes, right? You can glue that in or put that in your ring binder, in your Ringbuch, okay? Or you can just say, look in the book. But we'll put this very graphic, I'm going to put on Blackboard, okay? So some remarks about this figure there, about what you see up there, okay? First, a little bit, what is the most important thing? Where do I start? The most important thing is probably, let's start here. Okay. Each round, if you look up there, what I really want to show you is this here. This is round 1, this is round, let's say for AES with 128-bit key, we have 10 rounds. So this would be round 1, round 2, this would be round 9, and this is round 10, right? And the first 9 rounds are identical. So we do 4 things here. We do byte substitution, then we have what's called shift row here, right? Shift row. Then we do third mixed column, that's the third layer, and then we have a key addition layer. This is one round, okay? And then you do that 9 times. So let's just write that down. Each round consists of 4 layers. Where do we start? Byte substitution. It's sometimes just abbreviated at byte sub, byte substitution. Secondly, shift row. Sometimes they've written in one word, abbreviated, not shift row, but shift row without a Leerzeichen, without a blank. Mix column, or mix col sometimes. And fourthly, key addition. Okay, so, and now there are 2 things that are a little bit irregular, namely in the last round, to see the last round, you see that here, right? If you look at the last row, we have byte substitution, we have shift row, and we have key addition. What is missing here? Does anyone see that here? Mixed column, for whatever reason. So the last round is always a little bit special. Last round does not have the mixed column layer. Okay, so to maybe to start to motivate it a little bit in terms of theory or functionality, what do the layers do? And this is, obviously a large part of the lecture. You might vaguely remember when we talked about DS, we also talked about diffusion and confusion. You remember a little bit. And there's a direct map for that here. The byte sub provides confusion. Does anyone remember what was the confusion element in DES? Which part of DES provided confusion? Does anyone know? Anyone? Ein Sonderpunkt in der Klausur? Ja. No. Ein Minuspunkt. Okay, so no, I'm kidding. Anyone? What's that? Very good. The S boxes. So what's the S boxes? And byte sub is the S box layer. Okay, so this looks almost like this. This is an S box. There's nothing mysterious about it. Okay. Then other person said permutation, but permutation in DS don't provide confusion, but what is the other thing? There's confusion and diffusion. So these 2 layers together provide diffusion. And then key addition is something else, okay? So again, it's similar to this, that you can pinpoint this part of the algorithm that provides these 2 principles. What is also, which did not exist in DES, but which is a trend in modern block ciphers. In what you did in DES, we just had the Feistel rounds. What modern block ciphers often do, the first thing that what is the first thing that happens to the plaintext? The plaintext comes in, the 128-bit, and say, hey, I want to be encrypted. So the first thing what you do here, you add a subkey, okay? So you do that at the very beginning, and interestingly, you also do that at the very end, okay? And this is called key whitening, and this is a general principle that didn't exist in 1975 when DES was proposed. But nowadays, a lot of ciphers do that. This is called key whitening. I just want to write that down so that you've heard the term. So it would be, you should continue underneath here. At the end, at the beginning, of AES, and at the end, or at the very end, also ganz am Ende, at the very end, a subkey is added. And in quotation marks, this is called key whitening. I don't think there will really be a question on the exam about that, but if you stay in cryptography, you're going to hear the term key whitening more often. Okay, so this all looks very interesting, but the real exciting stuff hasn't happened so far. And I mean, the big question, obviously, at this point is, big question at this point is, what happens inside the layers? Okay, which is going to be maybe probably the main part of this lecture here. Okay, which brings us to we're done with the structure. So what we did so far, essentially, we talked about this figure that you see up there, the projected figure, and we talked a little bit about it. So now and we called this the structure of AES. Now the real interesting thing is what we call the internals is we want to look what happens to the bits. I mean, this is still very high level. You just have rectangular bar there and say, there's some manipulation happening with the bits. How do we manipulate the bits here? Okay, so this is the third section. Okay, and now comes kind of the most important. Now I'm going to do a pretty big drawing. So if you want to copy that, I think you need probably 1/3 of a page or half a page. But also, you don't have to copy it at all because it's in the book. Okay, so but just if you're copying, if you take lecture notes, wenn Sie mitschreiben, you need probably at least 1/3 of a page now. Okay. The figure number is very good question. It's 4.3, okay, figure 4.3. So what you're going to see is essentially a modified version of 4.3. I just wanted to slowly develop that figure for you. 4.3 is probably the most important figure, which is, in case you're wondering, this here, okay? So this is what happens inside around, but I could say this is how these are the internals, and let's do RSA, but we're not doing that, okay? So we're spending about 30 minutes on this picture here, okay? So what I want to do now, this is one round, and what I want to explain to you, what is the relationship of this drawing to this drawing, okay? So, but I want to stay with this for one more for 1 more minute. So note the 128-bit data path is split into 16 bytes. So this is a byte-oriented cipher, so almost all, I think all operations in DES operate on a byte level, on 8 bits, which is very, very different from DES. DES was a bit-oriented one. In particular, you did bit permutation, you had small S boxes. Everything in AES is always in chunks of 8 bits, okay? 16 bytes, and we know 16 times 8 is 128. So you take 128, you split it in bytes, you get a 16 out there. Okay. So, and now what I want to do, I want to start with one round. And I call the input to one round, I call A, which is a 128-bit vector or 16 bytes. Then just what you see up there, the first thing that we're doing is byte substitution. So that's a byte sub layer, die Byte Substitutionsschicht. And then we have the 3 other ones, which are quite interesting. And you should keep some space here, 4 Kästchen, okay? So, and then we get the first sublayer, which is called shift row. Then you get mix column, mix col, and then the 4th and last layer is key add, okay. And then you get the output, okay. So this is one round here, just to make it clear. This is one. This is one round. And so far nothing is new. It's just what we had before. And what I want to do now is I want to look into each of these layers. What's happening inside with the bits that we put in there, okay? The first byte substitution is very similar in principle what we do to DES. So what I do now is it takes this, I split A up in bytes, but there's 16 bytes, but the 16 bytes are again grouped. So I always look at 4 bytes, 4 bytes, 4 bytes, and 4 bytes, okay? I look at groups of 4 bytes. This is A0 up to A3. This would be, the next 4 bytes. I don't want to put all the names in here. This is the next 3 bytes, and here are the last 4 bytes, the last 4 bytes, which range from A15, 14, 13, 12, up to A12. Okay, A12, okay. So, these are the input bytes. Können wir leise sein? Das ist der harte, wichtige Teil. So what you do simply, and it's very similar to this, you take your byte here, you put that in your S box, which is, and I use circles here, which is maybe not that great. Okay, so you have an S box here, and the input to the S box is 8 bits, and the output is 8 bits. Okay, and you do that 16 times, so that means you have 16 S boxes, and they're all running in parallel. And just what we do, we call this here The output we call B, but this is not something that's standardized. This is just what we do in this lecture. You know, we call the input A. These are the A bytes, and after the S-box layer gets the B bytes out. So this is B0, and at the very end, you get B15 out, right? Okay. So conceptually, this is very simple. This is and again, remember, S stands for substitution. That means replacement, ersetzen. So you simply replace 8 bits that come in here with a certain value by another value. That's it. And this has something to do with Galois fields. We're going to see that in 15 minutes. Okay, we're going to talk about what happens there in more detail. So what is the next thing that's happening? And now I want to, I do want to switch to this this here. Okay, that's pretty visible. What the next thing, which is called shift row layer, sounds really fancy as though we were doing something really complicated. What this really is, this is just a byte permutation. So you're just reordering the bytes. Okay, you remember in DES we had a lot of permutations, but they were also always on the bit level. So individual bits were cross-wired. What you do here, you keep this byte structure intact. So you always take this one byte and now you put this byte somewhere. Okay, and the rule for that you see up there. Okay, so this goes into the mixed column box. We're going to talk about this. And there's a kind of a fun, but the actual shift row is this here. And what I meant to do is, because I like colors, I think colors are helpful. So, okay, this is that. The cross-wiring is what's called the shift row layer. This is just a byte permutation. It's nothing complicated. And this happens to be a value that we do have here. You know, the last one is coming from B15. And you do that 4 times. So you have 4 mixed column boxes here. 1, 2, 3 und 4. Okay, so you have 4 mixed column boxes, and each of that has some certain input pattern here. Okay. So. And each mixed column has 16 byte of input. Okay. And now I think I can, I'll do that at this point. So, you know, what I did so far, I just explained a block cipher, and I didn't give much motivation why we're doing that. And now I want to start to motivate it a little bit. Okay. One of the big features and very important features of modern block ciphers is we want to have diffusion on an algorithm level. What was that? Diffusion on the algorithm level means if I provide an input x0, let's call it x1. Let's call it x1. Okay. So 128 bits. Let's say all 0 bits. Okay. There's a certain key. What you get out is some ciphertext y1. You know, it looks pretty random. What we do now, again, imagine we have 128 zeros. Now you flip one single bit. Okay, so instead of 0, 0, 0, 0, you do 1, 0, 0, 0, 0, 0. Okay, let's do x2. Okay. What you do not want to happen is that y2 looks pretty similar to y1. Okay, I mean, the worst thing that can happen is that there would be only one bit that flips in y1, right? You don't want that to happen. So What you want to have is a y2, which again looks completely uncorrelated to y1, which this should look like a random number, and this should look like a random number, and there should be no relationship that you can exploit as an attacker. There should be no relationship. So this is called diffusion on the algorithm level. And let's start with this diffusion thing. I think it's a fun part to do, and it's a fun thing to do, and I think it's good for understanding crypto algorithms, symmetric algorithms. So let's imagine you put one input in here, 128-bit, and they run through the algorithm. What we do now, you flip one bit at this point here. Let's say first you had 8 zeros, and now you have a 1 and 7 zeros. 1, 0, 0, 0, 0, 0, 0. Okay? You put that in the S box, what probably, even we don't know that yet, but probably there will be bit flips here at the output, right? And as you can imagine, there are actually quite a few bits that flip here, okay? So you have, you go in with one bit flip, you go out with a few bit flips, maybe 3 or 4 bits have flipped, okay? This goes into here. This goes into here, but all the other, that means there's one byte where a few bits have flipped. All the other 15 bits are unaffected. Everybody with me? So right now, this is very local, right? One bit flips here, a few flip here, but it's really in the left-hand corner of the algorithm. What we now want to do, we want to achieve, you see that in orange provides diffusion. We want to get diffusion. That means we want to make sure that this, there may be 3 or 4 bits that have flipped here, that they spread over more than one byte, right? And what this mixed column does is the mixed column has 4 outputs. And what this mixed column makes sure is that these bit flips, which are local, which are only 1 byte, affect all 4 output bytes. Okay, that's the idea. And if everything works out, we get the following behavior. You flip 1 bit here, you flip, we don't know for sure, it depends on the details, but on average you have like 4 bits or so flip here at this point. You have 4 bit flips here, but suddenly, because this is bytes, this is 8, suddenly 32 output bytes are affected. Can you roughly follow? So this is very strong diffusion. You flip 1 bit here, and suddenly you have 32 bits affected. That means within one round, 1/4, 1/4 of the whole data path is affected here. So this is a very powerful property of AES that you have extremely strong diffusion here, okay? And that is the role of mixed column, and again, in 15 minutes, we're going to talk what happens inside, but this is a motivation. After the mixed column, which is color number 3, okay. Oh, and by the way, this is really, it sounds really complicated. You do a matrix multiplication. This is whatever. 11th grade high school, 11 Oberstufe erstes Jahr. This is not really very hard, how to do the mixed column here. So the key addition works exactly as you would imagine. You have 128 bits, right? You have 32, 32, 32, and 32. You have 128 bits coming out. The subkeys, the subkey ki, which you see here, right? This is the subkey ki. I can't highlight. I can highlight that. Okay. The subkey k. The I is gone. Okay, that's bad. So, you know what I mean. Okay, this subkey there. This is 128 bits, and you do a bitwise XOR. Very simple. So if you wish, at this point, you're bit-oriented. So what we do here, you do an XOR, and with key bit ki number 1, and it's a little bit too, it's hard to draw here. So ki number 2, and I'm not drawing all 100. I'm sorry. No, this is not. This is bytes. This is byte. No. This is ki. This is 1 byte. This is the first byte, or you can call that KA1, I guess. This is the first byte of the subkey and so forth. And at the end here, this would be ki, comma 16, right? So this is last byte of subkey. Okay. So that's it. 4 layers. So and again, if you look at the way we are learning about AES, so we started at this very high level, that this is a box with input and output bits. Then the next thing we saw is, which we didn't draw because it's too much of a pain to draw that, we've seen this here, say this is like this layered approach here, right? So this getting a little bit, this is much more detailed in the box you see over there, where you just have one rectangular. And now the next level of detail was this here, right? Okay, and this is what you see on the blackboard. But we're not really done because this is still very wishy-washy everything, right? So now the next thing that we do is we have to look inside the S boxes. We want to talk a little bit how is this permutation happening, and then we want to look into the mixed column. Okay, so but this is still all part of section number 3 here of the course of today. Okay, how do we proceed? So what we do, we start with the first layer, which is the byte substitution layer. So this is called it 3A. Byte substitution layer. I think it would be less confusing if people would have called it the S-box layer, but they didn't. So this is the S-box layer. And what the S-box layer does, you substitute on a byte level. So, you know, if you look exactly at the drawing up there, what's happening, you go in with some input bit AI, you know, A0, A1, A2, up to A15. You apply the S function to it, the substitution function. What you get out is byte BI. One thing which is quite different from AES, from DES is all 16 S boxes are identical. Okay. Again, this is different from DES. We had S1, S2, S3 up to S8, and there were 8 different tables. You know that from the homework assignments. This is different here again. Okay. So what about the tables here? The tables look the table look different, namely. Okay, so this is the no. Das ist 101. This is, I'm just looking for an S-box table. Here is the S-box table. Okay. Okay. This is similar, you know, it's bigger because there are more input and more outputs, right? It was smaller in the case of DES. So this is a This is table 4.3 in the textbook, in our book, okay? And first I give you an example how to read that table. This is just a question of notation. Example, let's assume our input AI has a value, and this is now written in hexadecimal notation, is C2, right, in hex. Now in order to read the table, oh yeah, and of course which we, you know, now we get X and Y. The first hex digit is X and the second is Y. So this gives you the X and Y coordinate here. So if X, what did I say? X is C, that means we're in this row here, okay? Everybody with me? Okay. And what is the Y value? Y is 2 here. So Y is here, so we get, and that means the output is here. You see where I'm with the cursor? The 25, okay? So that means BI is S of AI is, this is, you know, table. What did I say, 25? Okay. So far so good. So this is the way you read the table. It's actually, I think it's easier than the way you read the DS tables. And of course, we can look at that also on the bit level, which is, and DS we always only talked about bits, and you can do that here too. So for instance, we look at the binary representation of C. You know, C is the 12, right? Binary 12. So this is 1100. Let's see. C. And now the 2 is okay. So if this is the input to the S box, 11000, then the output here, now we rewriting B is 0010. This is 2. And 5 is 0101. So this is the decimal 5. Or hexadecimal 5. Okay. Means you go in with this bit vector, with this byte, you get this byte out. Okay, so this is how that works. Does anyone remember, in the case of DS, so we go back in time by 2 weeks, we had a similar looking table. It was a smaller table, but we had a table here for DS. Maybe I should show that. Let's look. I just want to look at the desk table again. Where's the desk table? Oh, we're getting close. Yeah, here. So that's the desk table here, right? This here. I'm sure it's fine. Okay, so in the lower left-hand corner, you see this is the S box table S1 for desk, right? Does anyone remember? And there are 8 of them. This is S1, S2, S3. Does anyone remember how they were constructed, where they were coming from? That was kind of the big secret they didn't tell us, right? And it turned out these you have to choose them in a very specific way to make them resistant against differential cryptanalysis. But how they were constructed, essentially, they had requirements, and then they chose a random table, and they looked whether the requirements were fulfilled. But this was early 1970s, so 40 years ago almost from today. When AES was designed about 12 years ago, people were smarter, and they knew much, much more about S boxes. And now what happens is that the S box has a lot of mathematical structure, which was not true for AES. This is kind of for DS. That's the point I wanted to make. There's a lot of mathematical structure, and actually a rather simple one. And this is what we want to want to show now. So now I want to go back to here. So it might be sufficient, and it's probably for the exam it's sufficient just to think, when you think about S-box, AES, you think about this table, right? Now, if you want to understand a little bit more advanced crypto, now I'm going to explain to you where this S-box is coming from, which I couldn't do for DES. This was really complicated. It turns out this S-box, the AES S-box, is constructed in a very specific way. And again, this is only people who are interested in somewhat more advanced stuff, okay? The question is, how is the S-box table constructed? Okay, so what you do, what we've just seen here, the input is a byte, of course, can be viewed as a bit vector, okay? And now finally we use Galois fields, something we spend a whole week on. What you do now for the S-box is you say, well, this is the input byte. Then you say, okay, so this is also a bit vector. And now you say this bit vector is a polynomial in the Galois field, is an element of the Galois field, okay? So what you do is consider AI element of GF2 to the 8. That means in this and that means this becomes a polynomial. I'll give you an example in a second. Consider a element of GF2 to the 8 and compute its inverse. Multiplicative inverse. Okay, so you do 1 divided by AI. So let's look at an example. And I made a mistake with this blackboards. I switch to the. So I do an example now, but I switch to the. To this here. Please continue. In your notes, just continue writing. So AI was this value, right? And now we make kind of, and I think this is conceptually, this is kind of a funny thing that's happening. These are really bits, and what we say now is, well, this can also be polynomial. That means you call this now AI of x, and this is, the zero coefficient, x to the 1, x to the 2, x to the third, and so forth. So this becomes a polynomial x to the 7 plus x to the 6 plus x. Okay? So this is a mapping bit string to polynomial in a very easy way, so there's nothing complicated. What you do now, you have to compute the inverse. Okay? It turns out that b of x, the output is x to the 5th plus x squared, x quadrat plus 1, which is exactly this bit vector. So now if you want to go transform that into bits, you get again this. Get again this here. Okay, so this is some kind of transformation or change of representation maybe. And now comes the important thing. So this was easy here. Well, what is the math behind this? The math behind it, this is the inverse here. So this is ax then is 1. And how is the inverse defined? The inverse is if you take the original element, a of x, if you multiply that with the inverse, which is x to the 5th plus x squared plus 1, which is b of x, which is the inverse, what do we have to write down here? $64,000 question. This is equal to what? Oh, excellent. But what happens if you multiply this out? You get a polynomial of degree 12, right? So this is 1, but under what else is missing here? Wenn ich das ausmultipliziere, kriege ich ein Polynom vom Grad 12 raus. Da kommt nicht 1 raus. What do I have to do? Model reduction, very good. Mod, and now the question modulo which polynomial, and I don't know, you might have forgotten that, but when we talked about Galois fields, every Galois field there are several irreducible polynomials out there. So for GF2 to the 8, there are a few dozen, I don't know, there are 30 or 40 irreducible polynomial. And there's one specific one which is part of the AES standard, which I gave you last week actually, which is x to the 8 plus x to the 4 plus x cubed plus x plus 1. Okay. So this is the, and I think I called it that even. So this is the AES irreducible polynomial. Okay. I made a mistake. Okay, so bear with me. Okay, so I made a mistake. I made a mistake. Okay, this is not the whole S box. Okay, so what happens in the S box are two parts. I'm really, really sorry. So you go in with AI and you compute little GF2 to the 8 inverse. This is what we just did, okay? What you get out of here is it's not BI but BI prime, okay? So and actually I was wrong what I told. Is that wrong? Yeah. This is not true here. I don't have BI. This is wrong. Okay, so this is wrong. That's embarrassing. Okay, so is this wrong? I have to look in my book. Yeah, this is wrong. So what I get out here is 5. This is different. So this is x to the 5. This is first thing. So what happens here? You have to do something else. You do the what's called affine mapping, affine Abbildung. And this is BI. So this is like an intermediate value, ein Zwischenwert. Okay, I'm sorry. And this intermediate value is, so this is BI prime here. This is x to the 5 plus 4 plus x3, x squared, x plus 1. And this is the inverse. I'm really sorry. Okay. So now here, you have to multiply this by, I'm sorry for the math. Okay, x to the 5th plus x cubed plus x squared plus x plus 1, and then you get 1 out. Okay? So this is the first part, what I did so far, this is the first part of the S box. Okay, and actually the main part. So I don't feel quite as bad, but it's the main part. Ja. Was genau ist die Frage? Nee, Binary stimmt nicht mehr, genau. Das war Ihre Frage. Ja, guter Bemerk, super, ja, genau. So. And this is BI prime again, BI prime. Okay. Again, I'm sorry, but this is BI prime. And what you want to do so you do this because you get very nice cryptographic properties out here. But on the other hand, you don't want to have an S box that has this very nice mathematical description because that could lead to an attack. So what we do next, this is followed by another transformation which kind of destroys this mathematical property, which I just want to show you. Which I only have in my book. You see this picture here? So now what I want to show you, what happens here in this affine mapping here. What happens in the affine mapping is this here. You see this BI. This is all 8 bits, right? What you do is you take those 8 bits here, which are called, B0 up to B7, aber Strich, right? These are the gestrichene Variablen. These are the prime variables here at this point, okay? And now you multiply that with this fixed matrix here. So this is, again, this matrix here, which I'm highlighting at the moment. This is part of the AES standard. You multiply, this is modulo 2 everything is modulo 2, and you add a constant vector. And the output of that is the actual S-box output, okay? So let's maybe go back here. So what happens within, what are we talking about? Talking about one of these circles here, right? Very, very small atomic component of AES. So what happens, 8-bit go in, the inverse is being computed, then you do this funny bit level matrix mapping, multiplying by a matrix, adding a vector, you get an output, okay? So, and I'm hesitant, ich zögere, even to explain that, because what the incorrect impression people might get, if I implement AES, what happens is that every time I'm implementing AES, back here, I have to do this really complicated Galois field multiplication, inversion, and all the other stuff. And now the question, why don't I have to do that here every time? I mean, you can do that, but why is that maybe not a good idea? What is faster? Yeah. You calculate it once because it's fixed, right? I mean, it depends on the input, but there are only 256 inputs. So you calculate it for all 256 inputs, and that's it. And it's even better, you don't have to calculate it. It's in the book, right? And it's on Wikipedia and everywhere, right? So, this is what here, this table that you see there, that was constructed in this really complicated way here, okay? That's why I said it's only for people who are really interested a little bit in the background. In the case of death, there was just this God-given table, right? It wasn't God-given, it was given by Don Coppersmith or whatever, right? But here, this is really complicated in a very clear mathematical way. And even better, if you're interested in hardware implementation, which is one of the things my group is doing for a living, in hardware, it's often actually better to compute that, because in hardware, it's sometimes not that easy to put a lot of small tables somewhere. So in hardware, often you actually do this Galois field computation. Okay, So this took a long time, but it was the hardest part probably. We're done with byte substitution. Now we want to look at the next function, which is shift row. And actually I can do that here. So this becomes section 3b is shift row. The shift row layer. To be exact, rows, plural. What do we do here? If you look at this diagram, if you look at this AES round, this looks pretty wild, right? I'm talking about this here. You see what I'm putting in the box here, right? You see this here? This looks pretty wild. Können wir ruhig sein noch, Viertelstunde? But it's very systematic. It looks very unsystematic and wild, like the death permutation, and some of them are pretty hard to understand. But here, there's a lot of system behind it. What happens here is that you very systematic. And you have to do you have to know the following trick. If you look at this in kind of in a linear fashion, what we do, right? The data path is kind of written in this way, which is actually the literature doesn't do that. This is only us who are doing it this way. In the literature, what they do is they take these 16 bytes, very systematic. If we write the state. And what is the state? i.e., das bedeutet, the 16 byte of the data path so this is, maybe I should have introduced that before. So when we talk of a really fancy way of saying the 128 bits inside AES is to call that the state, the Zustand. Okay, so these 16 bytes, the 128 bits, they're called the state. So the shift rows layer becomes very systematic if you write the state as a 4x4 matrix. Okay, so what does this mean? Rather than writing that in a long line here, put that in a matrix, and I'll show you what's happening. What happens then is here. Okay, so this is on the internet, right? This is on textbook.com, cryptotextbook.com. So this is the input: B0, B1, B2, B3, B4. So these are those 16 bytes. Okay, and what you do now, you take the first row and you don't do anything to it. You take the second row and you shift that one position to the left. It should be here. You take this and shift that by one position to the left, right? Like this. And you get this. Do you see this is the shifted version of this here? By one position. Can you follow? Is it too? It's not complicated, right? Same here. Now, for the next row, you take this row, B2, B6, B10, B14, and you shift it by two positions to the left. 1, 2. And the last row, surprise, surprise, you shift by 1, 2, 3. And of course, this is cyclical. Okay? If you do that, if you do this shifting here, and then you kind of unroll that, you get which is hardly visible, which is what you see there, right? And I'll show you. This, which I put in this box here, right? Which I put, is it too big? Yeah, this big box here, we see here, what I put in this thing. This is kind of the graphical, spread out representation, what you see in this matrix here. Okay? So this is just a byte permutation in a very systematic manner. Okay? And it's not, like everything in cryptography, almost everything, there's a reason for doing that. One nice thing is, for instance, these 4 bytes here, B0 to B3 here, you see they are influencing, if you follow the lines, they're influencing all the other mixed columns. So this 1 byte is going here, right? B0. B2, where's B2 is going? B2 is going all the way to this here. Oops. I understand that, okay. What's happening here? So B0 was going here, B1 is going here, B2 is going to this box, and B3 is going to this box. That means potentially B0 up to B3, which is here in the right-hand corner, these 4 bytes, they're connecting to exactly one of the other ones. That means they are spreading already over the data path. But this is not only true for this here, it's also true for this here. These 4 bytes are also, every byte is connected to one mixed column box. So this is connected to this one, B4 goes here, B5 goes here, B6 goes here, and B7 goes at this point, okay? That means each of these 4 groups of 4 bytes is always connecting to exactly one other byte at the output, okay? Which we need for diffusion purposes. Okay, so the last thing that's left, the last non-trivial thing that's left, we have to talk about mixed column. Okay. So, and let's go back to this Gedankenexperiment we had before, right? Where we said we flip 1 bit here. We have to be quiet for a few more minutes. We flip 1 bit here. There are only a few bit flips at this point. Maybe 1 bit flip here, maybe 4 bit flip here. We have only 4 bit flips here. And again, then the goal, and the mixed column is a very, very important element. Now we want to make sure that if you have a change at this point here, this is 8 bits, right? The few bits flip here, that all of these are somehow affected. And what you do for that, you do a relatively easy thing. Mixed column. Let's look at an example. Example is the first mixed column box. What I mean by first is the leftmost here. Die ganz linke here, okay? Mixed column box. So you have mixed column, your input, your 4 bytes input, which again, if you look here, what happens is it's coming from B0. The next one is B5, and then B10 and B15, which is also here. Oh yeah, here we can look, we just looked at the shifting. After the shift, this vector here, this becomes the input of the to here. Okay, so these 4 bytes. And then the output, we call in our notation here, we call that C0, 1, 2, and 3. And now the question, how do we compute that? And inside the mixed column, you just have a matrix multiplication. with a fixed matrix. So outputs, these are the outputs. The matrix I can also show you here. This is a matrix. There's nothing particular mysterious about that. This is a matrix here, okay? But I show you a way of, again, there's a system behind this. This is O3, O2, O1, O1. And now every row of this matrix is a shifted version of the next one. So this is O2, O3. What you do here, you write O2, O3. Then I shift that again, O2, O3. And I shift it again, I get O2, O3 would be here, but unfortunately it's the end of the matrix, so we wrap around. What about the rest? All the rest are ones, okay, or 0 ones to be exact. And this constant matrix is multiplied by B0, B5, B10, B15. Okay. And now it's not clear how do we multiply. What does multiplication mean? I mean, these are the first remark here is remark. All BI, CI, and constants are bytes. Okay. So all of that is 8-bit, right? Each thing is 8-bit. Okay. Are bytes. And now we have to do computation with that. So let's maybe look from linear algebra, how do we do that? And as an example, we look at C0, okay? And we just, multiply that according to matrix multiplication, right? This is O2 times B0 plus O3 times B5 plus O1 times B10 plus O1 times B15. Okay? Again, this is like 10th Klasse, right? This is matrix multiplication, okay? So, and what we would like, and each of that is a byte. So this is 8-bit. This is 8-bit. And even that is 8-bit in hexadecimal notation, okay? Any ideas? How should we multiply? What do we do here? How do we multiply? Is that integer multiplication? No, we would get 16 bits out, right? Namely, probably, which French mathematician am I waiting for? Whose name? Polynomial, this Galois field stuff. So again, we do this thing. These 8 bits become, we say this is a polynomial, this is a polynomial. Well, you multiply the polynomials and do modular reduction in this Galois field. That means it's very, very important that this is GF 2 to the 8 multiply, and this is GF 2 to the 8 add, addition. Okay. So the question that may arise here is, what are O1, O2, and O3, which are the cons, which are part of this matrix here, right? But this is answer. we just follow our convention saying these are bytes in hexadecimal notation. That means if you put them in a bit-oriented writing, so this is a bit representation. So this is GF2 to the 8 representation. I don't know whether this is some kind of mapping. So this is simply the 1. This is the 1 of the Galois field. Okay. O2 is getting a little bit more interesting. This becomes X. And O3 is probably the most interesting one, even though it's still pretty simple. X plus 1. Okay. So these are 3 polynomials. Admittedly, one is kind of a very specific, very simple type of polynomial. This is polynomial, this is polynomial. So what you do here, you do polynomial multiplication. 1, 2, 3, 4 times. You do 4 polynomial multiplication, followed by model reduction, of course, right? It's here with this is AES polynomial, x to the 8, blah, blah, blah. And then you do polynomial addition, and you get 1 byte out, and it's C0. Okay? So to wrap up the last statement for today is, again, we had this thing, some bits flip here. How can we assure that many outputs are affected? This happens through here because if there's a bit flip at B0, well, the bit flip occurs here, 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 and here. Okay? That means C0, C1, C2, and C3, they all depend on this byte here. Okay? And that's why you have bit flip suddenly in all outputs. Same here. Let's say we have a bit flip at B5. B5, is multiplied by these constants here, and suddenly again all 4 output bytes are affected. Okay, so because this is a square structure, input chain, if only 1 bit changes here, all output bytes, all 32 output bits are affected. So this is one of the few times I misjudged the time. So that means we only do the first 3 things, and decryption is being done in the Übung. Thank you very much.